Okay, we're going to talk about ellipses here, which are, in my opinion, a very, very close relative to circles. Well, actually, circles are a special type of an ellipse. So, this is an ellipse. It looks like an oval. It has certain definitions. It has a center point, which is important. We'll talk about that later. It's got a long axis right here. It doesn't have to be going sideways. It can be going up and down. It can be going on a diagonal. All the ones we're going to do are have the long axis either going left and right or up and down. And then it's got a short axis. It's going this way. They've cleverly named these. The long axis is called the major axis. The short axis is called the minor axis. And then these 2 points right here, point F and point E, are called focus points or foci. And all of these things have numbers and distances that are related to the equation that we're going to tangle with here in a little bit. But the important parts are the focus points, the center, the distance from the center to the outside edge in the long direction, which would be half of the major axis. So that's called the semi-major axis. Semi means half. Semicircle, half a circle. Semi-sweet chocolate, half sweet chocolate. And this would be the minor axis, and so this green line would be the semi-minor axis. And then the distance from the center to one of the focus points is, well, it's just that. So we've got the center, the focus points, these vertices at the corners isn't the right word, but at the edges of the ellipse. And those are all important things that we're going to talk about a little bit more here in just a moment. But first, I'm going to pause and to a different video. And we're going to take a look at this. It's off of YouTube. It's how to draw a perfect ellipse. It's short. I'm going to make it full screen. I'm going to talk about it. First, you'll notice that there is a couple of important spots here. These two toothpicks that are stuck into the whiteboard or desk or whatever it is, those are the two focus points. And then he's got this string that you'll notice that it's tied into a fixed length, and he's going to use this marker to start drawing it. So you'll notice that he's got the marker. He's going to stretch the string across the toothpicks. Well, you'll notice that it's got some slack to it, right? Notice how he kind of takes the marker and stretches it so that the slack is not in that string. Now the string hasn't changed lengths at all, not even a little bit. So I'm going to pause it there for a second. I want you to think about the length of this string here, which I'll call it maybe X, and the length of the string that's going underneath his hand, call it Y. You'll notice that X plus Y is equal to the same thing no matter where this pen is at. Right? If you take X plus Y, you still have the exact same value, whatever that value is. And we'll let it keep playing around. You'll notice that he's going to get this absolutely perfect looking ellipse because no matter where he's at, the length of this string plus this string is exactly the same. And he gets an ellipse. Ta-da! Isn't that wonderful? All right, enough of that. Let's switch back to something else. Hang on a sec. Okay, here I'm on this other website. You can see the URL up here if you really want to look at it closer. It talks about the reflective properties of an ellipse. So here you can see this blue ellipse, and these 2 points, A and B, are the focus points. And one of the properties of an ellipse is that pretend for a minute that this inside is completely reflective somehow or another, and if we originate, this is their big word, originate a ray at one point, it's going to come out of that focus point, and wherever it hits the ellipse, it's going to bounce off. You'll notice this tangent line right here in the green, and that these two angles are identical to each other. It bounces off of that tangent line at the exact same angle, and it's going to end up back at this other focus point. All right, then they go through a proof for it, and I'm not that interested in discussing the proof right now, but I wanted to bring down to this little applet right here where it shows what happens when you launch a beam, a ray, if you will, from any of these locations. And you'll notice that any point right here, this beam comes out, the tangent line would be coming right across through here where this arrow is. It bounces off at the exact same, and you'll see it ends up over here. If you aren't completely convinced of that, let's see, add the virtual image. You'll notice that these rays keep going out here and then bounce down. All right, if we move the focus points closer together, you notice what shape is starting to form. The closer the focus points are to each other, the more circular it is. The further apart they are, the more, I don't know, flatter it is. And if the beams launch out, they all do the exact same. Anything that's coming out of here gets reflected, and it ends up in this other focus point. So that's one of the properties of an ellipse. And in fact, there are whispering galleries. If you want to take a little YouTube adventure, look up whispering galleries, and you can find some interesting things on rooms that have been built with this property. It's very strange. All right, I'm going to pause this video again. Here's another animation that I found online someplace where it describes what's happening. You notice all these little particles that are popping out of one focus point and are traveling across the ellipse. Notice how as they travel, the path that they're following, they're all traveling at the same speed, but they follow that circular path. So imagine a sound wave. Somebody standing at this ellipse inside of a big blue room, somebody standing right here at this focus point, and they say something. Well, the sound starts coming out of their mouth in all different directions at the same time. When it hits this wall over here, it bounces and reflects and starts traveling this direction. And as it comes past here, now clearly the person standing here is going to hear little tiny bits of the sound wave, but you'll notice that as they all come across and bounce, they reflect, and they get stronger until, bam, the person right here can hear everything this person says as if they were standing right next to him. Again, search on YouTube, look for whispering galleries, find some videos of it. It's very creepy, weird what you're going to find out. All right, I'm going to put that away, and I'm going to continue discussing some things about this ellipse right here. All right, first of all, I've got this formula entered into this program. And so it's actually graphing x minus h, which is right down here, h. You'll notice as I change this value, the center is moving. And y minus k, here's k, and it's moving. But a more interesting part to me is this value a equals 4, which is the number underneath the x, and b equals 2, which is the number underneath the y. You'll notice that when, again, these 2 points get to be exactly the same, b is 5, a is 5, I get a perfect circle. This length here is 5. This length here is 5. Okay, so I'm going to change it back because ellipses are really pretty easy to understand in many, many ways. Here the number a underneath the x minus h term is 5 squared, so it's 25. Well, I know that this distance from here to way out here is 5. And I know the distance from here to here is 2, because the b is underneath the y. Okay, or the 4, which is b squared, is underneath the y term. Okay, so I change this. Say maybe I make the a 6 and the b 4. Since there's a 6 squared underneath the x term, I know that the distance from the center out here is 6, which means all the way across, this whole line all the way across, which is called the major axis, has got to be 12. 6 here, 6 there. And this distance here has to be 4, because this is 4 squared, or 16. Okay? Now we'll come back and talk about this focus distance here in just a little bit, but so far, so good. I'm going to pause this recording here again and switch to something else. Okay, so here we are. One of the notes that I was going to fill in class here. I'm going to talk about this equation right here. It's clearly an ellipse because I've got this plus sign right here. That makes it an ellipse or a circle. But because these two numbers are not the same, this number here and this number here are not the same, that means that this is definitely an ellipse, and it is not a circle. But here's what I can tell. The center of this particular ellipse is at -3, 1. So as I graph this out, I would go out and say, call that -3, and that's 1 right there. So that's my center. And since this number underneath here is a nice, beautiful, perfect square, I know that this is a squared. And guys, I don't really care which one's a and which one's b. The important part is that it's underneath the x. So if that's equal to a squared, then a must be 10 in the x direction. So what I'm going to do is count out 10 units this direction. So that's 3, so 4, 5, 6, 7, 8, 9, 10. So it's 1, 2, 3, 4, 5, 6, 7. And that must be one of the vertices. And then I got to go 10 units the other direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I'm off the screen. It's over here. Who cares? I've got the idea. This is that one axis right here. That's the major axis, A equals 10. B is equal to 36. I'm sorry, B squared is equal to 36, which means that B is equal to 6. And that, because it's underneath the y term, that means it's in the y direction, up and down. So I'm going to count up. Let's see where this was my center point right here. I'm going to count up 6 units. So 4, 5, 6, 7. 6 units this way. And then 6 units down. So that should put me down here at 5. And of course I'm going to go ahead and label all these points. -3, -5. This was at 7, 1. This was at, let's see, it was at -3, I was at 1. I went up 6, so that was 7. And this guy over here would have been at 10 units away from -3, so -13, 1. And my ellipse would travel through all of these points. And of course, you'll forgive me if my drawing isn't great, because my drawings never are. Yeah, it's close enough. There's my ellipse. Now, obviously, my focus points have to be someplace in here. I don't know exactly where, but they're going to be along that line. And that brings us up to the next important discussion that we have to have about focus points. Yay! So we've got our major axis right along here is 20. Major axis is 20. The minor axis, the shorter axis, pretty clever names, right, is 12 units. The vertices I've got all listed out there, all of them. The major axis vertices, the minor axis vertices. The only in the center we've got is -3, 1. Okay, the only thing that we need to do then is to figure out what the focus points are. Here's how it works. It's easy squeezy, nothing to it. The Pythagorean theorem is the key. I just remember the Pythagorean theorem, and I use a little bit of reasoning. Okay? Now, for whatever reason, somebody decided that they were going to call this distance from the center to the focus the value c. Okay, so in an ellipse, which one of these three is going to have to be the biggest? A, the distance from the center on the major axis, or B, the distance from the center to the minor axis, or C, the distance from the center to the focus point. Which is going to have to be the biggest? You tell me, A, B, or C? Anyone? Anyone? Yes, that's right. A is always going to be bigger than C, no question about it. And A is going to have to be bigger than B. So since A is always the largest, that means this is how it's going to have to fit. That A squared would have to be equal to B squared plus C squared. Now I could show you that this really does work if we wanted to make a triangle, but you'll just trust me, I'm sure. So I'm going to go back up here to find out about the focus points, because that's what I'm interested in now. And I'll do this work down here, where I know that A squared is equal to the other two numbers squared. So A squared was 10 squared, and B squared was 6 squared, and C squared, I don't know. So I get 100 equals 36 plus c squared. So that's equal to 64. So c must be equal to 8. That means that from my center point, I'm going to move 8 units this direction, which should put me right here. That's focus point 1, I'll call it. And let's see, that was -3. I added 8, and it should be at the y-coordinate of 1. Oh yeah, so that's 5, comma 1. And in this direction, it should put me over here at focus point 2, which was -3 minus 8, comma 1, or -11, comma 1. And there it is. All right? So far, so good? Excellent. I'm going to pause the recording while I set some stuff up. Okay, this is going to be the end of this particular video. What I want you to do is take a minute, write this equation down, graph this equation, finding all of the points, the endpoints of the vertices, the focus points, everything. Make a good sketch. And then in the next video of this section, you can check your answer. There we go.